Adversarial examples is a topic that is highly discussed among researchers nowadays. Most people conducting research in the area, however, seem to be experts or have at least deeper knowledge about the domain. Some attackers might not have this knowledge, but they are still attempting to attack machine learning models using adversarial examples. My colleagues Felix Freiling, Ramin Tavakoli-Kulagari, and I have tried to find an answer to the question whether or not adversarial examples can be created by people without any knowledge about machine learning. What we are looking at here right now are two example images that were created by our own adversarial example algorithm. We can see that especially the red image has some significant perturbations. Three main criteria we noticed are most important to define whether or not an adversarial example algorithm is good. Seem to be, first off, a high misclassification rate, which means that the adversarial example algorithm is able to find adversarial examples that have a lot of images misclassified. The adversarial examples should be imperceptible. That means that they are almost non-perceptible and compared to the original image should look the same to the human eye. And last but not least, adversarial example algorithms should be stealthy, such that they do not need to access the targeted classifier very often. These three criteria have a trade-off, which means that for a high misclassification rate, one might need more perturbations, which means that the perturbations might be perceptible. If one tries to create adversarial examples with small perturbations, they might require more queries to the classifier, such that to find the decision boundaries and to clearly define and find small perturbations that are yet successful. Different from other research so far, we did not try to find the perfect adversarial example, but just to find adversarial examples that are successful with an algorithm that is easy to implement even for people who do not have any deeper knowledge about machine learning. And our algorithm basically does the following. Here we see a pool of images taken from the MNIST dataset, and for each image that is queried from the targeted classifier, our adversarial example algorithm picks up the probabilities and the image itself and queries images with small perturbations. We call our adversarial example algorithm simply AE algorithm. It works in an iterative fashion, such that in each iteration it creates copies of the original image in the first round, or in any other round, the temporary, not yet adversarial example from the previous round. And in each copy, it perturbs one pixel, and this pixel is picked randomly. We call these copies with the small perturbations candidates. All candidates are then queried from the classifier to receive probabilities. And these probabilities are analyzed to find which perturbations contribute in a good way to the classification result. And good in this case means, from the point of view from the attacker, that the perturbation of the true label is reduced. On all these perturbations that reduce the probability of the true label are merged into the temporary adversarial example, which is then used in the next round to create copies and candidates from. This whole procedure is repeated until either an adversary example was found or the maximum number of rounds is reached. Here are two more examples that were created by our adversary example algorithm. They were classified as a 3 and a 2, even though the numbers are still clearly recognizable, but at the same time the perturbations are also clearly recognizable. A human not familiar with the concept of adversary examples might discard them and not see them responsible for the misclassification. We noticed one interesting thing while running our algorithm. Imagine we have the first round of the algorithm. We have an image we would like to turn into an adversary example, and this image is classified correctly by our algorithm with a probability of 99.8%. The algorithm creates candidates and receives all the probabilities for the true class from the classifier. We can see that for 3 of these images, the probability of the true class is reduced, while the 4th image has an increased probability for the true class. This image will not be used in the next step. It will be skipped. So the first thing the adversary example algorithm does is to rank all these perturbations according to the implications they have on the classification result. This means that the second image or second candidate is now the first image that is to be merged into our adversary example, and so on. The third candidate that contributed to the probability such that it is increased will be skipped, as I mentioned earlier. So here we have our original image, which could also be the temporary adversary example that resulted from the previous round. And it has a probability of 99.8% for the true class. We merge the first perturbation to it, which is the same as the candidate right now. Like the candidate and the merged image after the first merge was successful is the same image. And it has also the same probability of 99.5%. We then merge the next perturbation. The probability is reduced slightly to 99.4%. And now we merge the third image. And interestingly, the probability is increased slightly to 99.6%. And this is what we call the merge drift. And merge drift means that two candidates, which both result in a smaller probability for the true class, result in a higher probability for true class, that or a probability that is higher than at least one of the candidates' probability when merged together. And this will result in a lot of images or perturbations that are merged into the temporary adversary example that do not contribute in the way the adversary would like to, but in the opposite direction, such that they increase the probability. So it is important to optimize the merge drift. And we did that by running several experiments. And in each experiment, we increased the number of pixels that are perturbed in each round. And the number of pixels is influences the amount of candidates that are created in each round directly. And here we see the resulting graph. Important are the two dashed lines. One is the purple line that starts at 100%. The dashed lines refer to the right axis. With D is 1, we start at 100%, which makes sense. We only merge images that really contribute to a smaller probability for the true class. Then it decreases steeply before it flattens. Interestingly, the misclassification rate, which is the red dashed line, seems to mirror this behavior slightly. It starts low at around 90% and then increases sharply before it flattens and stays at 100%. We decided that the best D is the D that has a the highest possible percentage of successful merges, but still results in a misclassification rate of 100%. So this means as soon as the red graph reaches 100%, we will pick the D, the smallest D. And in our case, this would be 10, here for CFAR 10. We also did the same experiment on MNIST, and we got a similar result of the graphs, but for MNIST, the best D was 50. Another thing we did to improve our algorithm was to decrease the search space for random pixels. And we did that by using masks. Here are the masks we used. We had two main types of masks. One was the center mask, and then we had a frame mask. The dark area is the area that is perturbable, and the brighter area or yellow area is untouched by the adversarial example algorithm. We have masks in different sizes, 25%, 50%, and 75%. Those sizes do not refer to the number of pixels in the mask, but the width and height of the image. So it's 25% of the width and 25% of the height. And our experiments then result in the following. On CFAR 10, we have almost no difference in the misclassification rate. There is a slightly worse misclassification rate for center 25% and frame 25% masks, but overall it stays pretty close. The center 100% mask is the normal image. There is no restriction in the search space. By the way, then we see that the mean absolute error and the average number of queries to the classifier differs significantly. The mean absolute error is reduced for some masks. We can see that the frame masks perform overall worse than the center masks. And the best center mask seems to be the 50% center mask, even though it has a slightly higher mean absolute error than the center 25% mask. It still has a higher misclassification rate, as the center 25% mask has a tiny, slightly worse misclassification rate. Average queries shows the same. In this case, we have center 50% has the smallest number of average queries. Center 25% has a higher amount of queries. And again, the frame masks perform worse than the center masks. Here are some example images. These are the ones we saw earlier. And here are the perturbations we added to the images. These are highly saturated, so we are actually able to see which pixels were perturbed. And the top image has only 3 pixels perturbed, and they are almost non-perceptible, or are indeed non-perceptible to the human eye. The bottom image has a few more pixels perturbed. And yet we think a human who is not familiar with the concept of adversarial examples might discard those perturbations. To see if our improvements also have an effect on other adversarial example algorithms, we picked local search adversarial example algorithm by Narodinska and Kasiviswanathan, which we refer to as NK in the following. Their algorithm is similar to our AE algorithm, but it is time preserving, which means they perturb pixels only in one direction. And they also always perturb pixels that are in close proximity of previously perturbed pixels. We improve the algorithm by first optimizing merge drift and second using masks. We ran their algorithm ourselves by using the implementation that is included in the full box library for Python. Here are our results for the original run according to the settings and parameters they mentioned in their paper. The number of pixels that are perturbed in each round is 5, and center 100% is the full image. The mask does not restrict any pixels from being perturbed. We first use our optimized merge drift, which means we set D to 10. And we can already see that the misclassification rate is slightly improved, while the average queries to the classifier are also improved, namely reduced. The mean absolute error, however, is increased. Previously, we have seen that masks reduce the mean absolute error, so let's apply some masks. Here we see our center mask, and we see that the mean absolute error in the top left is indeed reduced again. It still is higher than in the original run, but it is smaller than after our first improvement. We also increase the misclassification rate further. Center 25% does not perform as well, but the center 75% and the center 50% masks perform very well. They also reduce the number of queries required, especially the center 50% mask. So in general, we can say that improving NK is possible by using masks and optimizing merge drift. To sum up, we discussed quality criteria that define whether or not an adversary example algorithm can be considered good. We proposed our own adversary example algorithm, which we call AE algorithm, that can be implemented by people who have no knowledge about machine learning, as it treats the machine learning model as a black box. We introduced and optimized merge drift and showed the effect of bit masks on the search for adversary examples. Some topics we would like to discuss in the future and analyze further are, first off, we only tested our adversary example algorithm on small images so far, namely MNIST and CIFAR10 dataset. It would be interesting to see how it performs on larger images, such as images from the ImageNet database. Also, the results are often rather similar, especially regarding the misclassification rate. So we are wondering if this is still statistically significant, but we think it will be more obvious when using larger images. Then merge drift and mask do not improve all adversary example algorithms. We attempted to improve several algorithms that we could find online, but we were only able to significantly improve NK and improve one or two quality criteria of a few other algorithms. We think merge drift and masks mostly apply to adversary examples algorithms that use a local search or a random search procedure. And last but not least, we would like to analyze the effect of other mask types as well. So far, we have only used frame and center masks, but it would be interesting to see how other masks affect the algorithm. For example, one interesting thing would be to use masks from explainable AI techniques, such as LIME, that outputs a mask that highlights areas that are important to the classification result according to the classifier. This would be really interesting to have a look in the future, which we will attempt to the best of our knowledge. That being said, thank you very much for your attention, and I will be taking your questions now.